In today's session of parallel programming, we will be moving on to the next topic related to send and receive commands in message passing interface. We have already seen the basic program structure for message passing interface. Now we will move on to MPI communication, how it is actually done, how the process will communicate from one process to the other process. So this MPI communication can be done in two ways. One is your point to point communication, or you can call it as process to process communication. The other one is collective communication, where a group of process will be involved in communication. And coming to this point to point communication, where you have only one sender and the receiver, this can be done in two ways. You can either go for using blocking communication or non blocking communication. So, in today's session, we'll concentrate on point to point communication, how blocking communication is done, and how the non blocking communication is done. Collective communication will be seeing in the next session. Coming to point communication here, as you can see, you have a sender mailbox, you have a receiver mailbox, and this is your actual message that you want to transfer from your sender to receiver. So what are the things that are being required? So you require a buffer where you can temporarily store the data, and that data can be sent to the receiver. Similarly, after receiving the data from the receiver, you have to store the data somewhere. So you require a mailbox at the other end for receiving the data. And when you see this message, we can even call it as an envelope. We have three parameters for it. Rank indicates ID of a process. Each process in the communication world will be given some number ranging from 0, 1, 2, 3, 4. So this is an ID to a process, so that we call it as a tag. Sorry, rank. And tag is nothing but an ID given to a message. So when you are sending multiple messages across A to B, and you want to identify the messages, so each message will be having some number associated to it, that will call it as a message tag. And communication group is nothing but you have n number of process dealing it, and how many process are being involved in the communication is related to your communication group. Now, coming to the first type of communication here, blocking send and receive. As the name implies here, blocking. Blocking in the sense when you have a process A and process B. Now, see, process A has done some amount of work till here. You can see this particular box. And now it wants to send the data. Now, the data is ready with process A. It has to send the data. So, it will be requesting to send the data. But here, when you see, process B is busy doing some other work, so it did not get any acknowledgement from the B saying that you can send the data. So till it gets an acknowledgement, this particular process A will be not doing any work, but it will be just waiting for process B. And once process B has completed the work, it just sends an acknowledgement saying that you can now send the data. Then it will be preparing a message, and that message would be sent. So this amount of time, the process A is simply waiting for process B. So process A is blocked. It is not doing any other work. It cannot continue the work until it says that you can send me the data. When you go for blocking communication here, we can either have blocking receive first, blocking send first, or alternative send and receive. So when you go for blocking receive first, so first you execute a receive process, where this receive process will be blocked until it gets the data. So when you go for any of this process, so this process will be blocked waiting for the data. When you go for blocking send receive here, send receive, so it will send the data, and if the buffer is available, it will copy the data and continue. Otherwise, if the buffer is not available to send the data, it will be just waiting for the buffer to become empty. And you can even have a alternate send and receive, where first the process will send the data and it waits till when it waits till the data is being received by the receiver. So until it gets an acknowledgement, the sender will be in a block state. Similarly, if the receiver wants to receive the data, it will be just waiting for the sender to send the data. So you can either go for blocking receive first, blocking send, or you can go for an alternative of send and receive. So when you go for blocking communication here, we have a function MPI underscore send. It is a predefined function which is present in MPI.h. And this MPI send function will have the parameters buffer. So if I want to send the data, you require data to be stored somewhere, right? So this buffer, it's a pointer to the buffer where your actual data that is to be sent is stored, and count the number of elements you are sending in the send buffer and the data type of each of the element that is being present in the buffer. And this is the rank of your destination. The tag, it's an integer value which indicates the ID of the message, and this is your communicator. So when you go for communicator, we go for using a default thing, MPI communication world. So you can, instead of this MPI com, we can just write MPI communication world. It indicates the communicating process. Similarly, when you go for blocking communication, after you send, you have to even receive your data, right? So when you want to receive your data, you even want to have a buffer, the same number of count as of your sender, the data type, and here you mention the ID of the source which is sending, and the tag is an ID of the message, and again the communication world. And if you want to know the status about what type of messages are received by the receiver or any type of error code, you can go for using MPI. You can use a pointer in place of your status. If you can just see the sample program here, it is mpi.h, and this is your normal C program which we'll be using. These are your command line arguments. Here the data I want to send is 42. And we even create a buffer for your receive. And since you want to start your MPI communication, you have to go for MPI initialize and pass your argument and the vector value. If you want to know the rank of each of the process, you can just go for using default communicator MPI communication world, and the rank value will be stored in this pointer. You can even know the size, number of processes that are involved in the communication by MPI communication size. And the reason why am I including this condition is if you have less than 2, so sending is one process, receiving is other process. So compulsory you need to have two process. One will send, other will receive. So if it is less than 2, this program will not be working and you are just finalizing it. I mean, you are stopping the execution. Otherwise, if the rank is 0, you are designating it as a sending process, and we go for including a function send. So where is my data stored in data send? And this is the number of elements you are sending. I'm only sending one element and the data type of it is this. And this is the destination ID. This is the tag of your message, and this is your communication world. Similarly, when you are going for your receiver, we go for executing a function receive. The received data will be stored in this address specified, the same one element. The data type is integer. The source value here is from where you're getting 0. So 0 is your source and 0 is the tag. And communicator world, MPI communication world, and MPI status ignore. If I don't want to know any of the status, either related to your error code or related to your tag, you can just write MPI status ignore and you go for finalizing it. What is the problem with blocking communication? So as you can see, one process will be just waiting for the other process. So you can get a situation of deadlock. So you get a problem of deadlock. Or else the process which is waiting can waste the computational resources. So it has the CPU and all the resources allocated, but it is simply waiting for some other resource. So to overcome this, so wastage of computational resources and deadlock are some problems. To overcome that particular problem, we'll move on to non-blocking send and receive. So when you go for non-blocking and send and receive, you see process A and process B. Process A, after the work is done, it wants to send the data. So it will just send a request and it will not wait for process B. It continues with other work. So once process B is ready, it sends that you can send me the data, then it sends. So here in previous case, this process was simply waiting, but here you can just do the other work. So you're not blocking the process. And the functions which we'll be using here is MPI iSend. Previously we were using send. Here it is iSend and iReceive. And in order to make a process to wait, we'll just go for wait and test whether the process has been completed the operation or not. We go for test. So when you go for MPI iSend, it is a pointer to the buffer where you are actually storing the data, the number of values you are storing, want elements you are sending, the data type of it, the destination ID either 0 or 1, the ID of the message, communication world, and this is a pointer to the request. So here this will contain the address of the object which has made the request. So it contains the address. So if it is a source, so it contains the address of the source which has made a request. Similarly, at the receiver side, you even have a buffer storing the data, count the number of values you want to send in the buffer, the data type, the source ID, the tag related to ID of the message, the communicator word here, and the request. Now, when you are going for MPI wait, if I am executing it at the sender side, this is a pointer used by the sender or the receiver, and this is a status. As we told you, if you don't want to use the status, you can just write MPI status and ignore. MPI test. So when you go for MPI test, you are making here MPI wait, you'll make a process to wait if you want. And if you want to check whether the process has been the waiting condition has been met, you can just go for testing it whether the condition of waiting is met or not. Now, when you go for the actual program, how do you write it? This is your data send and data receive. This is your initial thing. The communication rank and size will be same. We'll actually see MPI send. So MPI send, the data you are sending, how many values you are sending, the data type, the destination, the tag of the message, communication world, and this is ampersand request. So after you execute this, the address of this particular object will be stored in this request field, and this is at the receiver side. So you have initiated a non-blocking receive. So if you want to wait, if you want to make the process to wait, if you want to make any of the process to wait for execution to be done, it is non-blocking, right? So it means that process A, after giving a request, it can continue the work, but in some situation you want this process to wait. So in that case, we can just write MPI wait. It is an address of the request which is being generated, and here I don't want any status to be reflected, so we can just write MPI status ignore. And if your rank is equal to 1, you are saying that your data is being received, because 0 is designated for a sending process and 1 is received for your receiving process. So you are making this process to wait. So once it is waiting, sender process, the data is being received by your receiver process. So you are making the sender to wait here. Now, what are the advantages of your non-blocking communication here? Overlapping means that you can even go for computation and communication overlapping, meaning that you can assign the work and do the remaining work. And reduced synchronization overhead, you need not wait for the other process. You can continue with your work. Minimized potential for deadlock, there will not be any case for deadlock, and better load balancing. Better load balancing is you are assigning the work to something and continuing with the other work. So you are not making it, ultimately all of this will deal with, you are not making a process to wait, mean that the work is equally shared. And network utilization, it will also be done in a better way. Now when you want to see, have you seen the sample programs? When you want to execute them, well, first you go for installing your Visual Studio, and additional to Visual Studio, you have to download MS MPI SDK. And after you install them, if you want to check whether they are being installed or properly, you can just type it as set MS MPI. So it will give you this, so indicating that it has properly been installed. Now, after that, in the Visual Code, you go to your C++ environment in the General tab. Coming to your additional include directories, you go for including MSMPI x64, meaning that it is a 64-bit, and if you want it for 32-bit, you can set it as 32. So this is to be done explicitly by the user. And in the next, if you want to go for linker options, in the linker, go for your all options. In linker, all options. Then in additional dependencies, you go for including it as MSMPI library, msmpi.library. So additional to this, you need to include it as msmpi.lib and give a semicolon wherever you are inserting. And for additional library directories also, you can write it as $msmpi lib 32 for 32-bit, otherwise it is lib 64. Having done this, you'll be coming back to your command prompt. At the command prompt, you need to come to this your debug folder, write the code in your Visual Studio. After writing the code in the Visual Studio, you build up the code. After building up the code, at the command prompt, you write mpi exec -n is your first argument. It indicates the number of process. So here the number of process are 4. And then you write the executable file name. This is what you already write it in your C code. And then since you have specified it as 4, you will be getting the output from 4 processes. So this is how the blocking and non-blocking communication will be done using your MPI.